We are Electrical Engineering Team 2127. My name is Liz.
I'm Paul.
And I'm Aaron.
And this semester, we worked on the passive acoustic array design for environmental monitoring. The U.S. Navy often tests undersea devices and explosives in local waters. However, they must first survey the area to ensure the safety of wildlife. Currently, they use acoustic hydrophone arrays to identify the directions from which animal sounds are emitting. However, these commercial hydrophone arrays are expensive to set up and maintain, difficult to calibrate, and subject to signal interference. Furthermore, although they can identify the direction of arrival of different sounds, they cannot determine the identity of the sound source. Ideally, the Navy would like to create a device that may mitigate some of these weaknesses. Due to a limitation of a lack of access to an ocean environment and biological similarities between whale songs and bird calls, we are starting out with an analogous array for birds. For this project, our array will record audio in an outdoor environment and will identify the direction of arrival as well as the species of bird calls within the recording.
The physical component of this project consisted of an 8-channel time-synchronized microphone array. We found and tested the matrix voice array, which has 7 microphones arranged circularly, with an 8th in the middle. Having multiple channels is crucial for the beamforming and direction of arrival algorithms discussed later. This array is connected to a Raspberry Pi for higher level control and storage of audio to an SD card in an accessible format. Some of the specific properties and specifications of the array can be found in the table on the right. Additionally, in order to ensure successful recording and analysis of audio, a couple of other hardware components are required. One of these is a protective case. This case is made from a 3D printed shell and is covered in an acoustically transparent foam. This case dramatically reduces wind noise and it protects against light dew in colder weather. Also, knowing the temperature is required for accurate beamforming and direction of arrival calculations. This sensor, the AHT20 temperature and humidity sensor, connects to the matrix and Raspberry Pi via I2C bus. A script samples the exterior temperature every 5 minutes and saves a timestamped sample to a file. The timestamps on the file help to align temperature samples with audio files for later processing.
The second project deliverable was the working beamformer and direction of arrival algorithm. Our goal for this algorithm was to transform the 8-channel audio captured by the array into beams of audio in a single channel projected in given directions. This allows us to increase the signal-to-noise ratio for bird calls not close to the array. During the first semester, we focused on building and testing 3 beamforming methods. The final method we settled on was building a custom fractional delay finite impulse response filter to approximate time shifts before mixing the channels. This method was a great balance of speed and accuracy. The third major project deliverable was our classification method. We decided to use a multi-model approach using an identification model to isolate sections of audio with birds from sections without birds, and a second stage classification model to label types of species. During the first semester, I defined custom features and built a single model identification model. This semester, I expanded this by ensembling our GBM with new random forest and BART models to reach a final area under the ROC curve of 86.28. This performance matches some of the highest performing models in a recent bird detection challenge. The final stage of our modeling approach was designing our custom classification method. Since we did not have much training data, the first step was to build a synthetic dataset of birds common in Northeast United States. For each clip, I mixed white noise and generated a spectrogram of the first 5 seconds. After optimizing my classifier, we were able to achieve a micro F1 of 63.54. This score is a fantastic result and would be a top 2% submission on a recent Kaggle competition focused on labeling bird calls. The image on the right shows one of the processed spectrograms for a northern cardinal.
Our fourth and final deliverable was to collect a 24-hour continuous environmental recording using the 8-channel device. We use this to further validate our direction of arrival and classification algorithms. We manually determined the expected outputs for a sampling of the recording to use as ground truth for this validation. Additionally, this dataset will be useful for future design teams that continue this project. We would like to thank our advisors and our sponsor.